The objective of this lecture is to provide an example of setting up a system of differential equations in first order form, and then to show the basics of how to implement the system of differential equations when solving them numerically using Matlab. Let's start with the following simple example. A particle moves in 2 dimensions under the influence of gravitation. So we have a point, O. We have a basis, EX, EY, and then out of the page is EZ. And this basis is fixed in the inertial frame, which I will denote I. This origin at point O is also fixed in I. Now we have a particle of mass m, p, and the position is measured from O. So this is the position of p relative to O, and this particle has mass m. The distance from O to p will be denoted as r. The angle between EX, which is fixed in the inertial frame, and this position of p relative to O will be denoted theta. Now I'm going to set up a second basis. That second basis is going to have UR along OP. UZ is going to be out of the page, which is also equal to EZ. And then U theta is the vector that completes the right-handed system, and it's equal to UZ crossed with UR. Now, that's the starting point. We're going to do the kinematics and we're going to do the kinetics. Now, imagine that this point O is some mass. I'm going to call it big M. Okay? And the only force that's being applied to the system is the force of gravitation applied by big M on little m. So that's the kinetics part of the problem. Well, we're going to go through the kinematics first, because the kinematics are going to be important when we're actually trying to set up the problem first in second order form, and then be able to take that same problem and be able to transform it or transcribe it into first order form. And we have to go through Newton's laws to be able to do all that. So we'll do that now. So first, let's do the kinematics. Now we're using r and theta to describe the motion of the particle. So the position of p relative to O is equal to r UR. Now, I'm going to say, just arbitrarily, it doesn't really make any difference how I denote this, but I'm going to say that UR, U theta, UZ is fixed in a frame I'm going to denote as A. Now, because A is different from the inertial frame, in order to be able to compute the velocity and acceleration of P as viewed by an observer in the inertial frame, we have to take into account the fact that A rotates relative to the inertial frame. So that means we have to apply the transport theorem twice. So the first step here is to get the velocity of P in the inertial frame. Well, that's the rate of change in the inertial frame of the position of P relative to O, which is equal to the rate of change in A of the position of P relative to O, plus the angular velocity of A and I crossed with the position of P relative to O. Now, going through the kinematics at this step, d dt and A of the position of P relative to O is equal to r dot UR, because UR is fixed in A. The angular velocity of A and I is theta dot UZ crossed with r UR. So this gives a velocity, as viewed by an observer in the inertial frame of point P, of r dot UR plus r theta dot U theta. Now, the next thing I'm going to do is I'm going to compute the acceleration. So the acceleration of P in I is equal to the rate of change in I of the velocity of P in I. Now, that's equal to the rate of change in A of the velocity of P in I, plus the angular velocity of A in I crossed with the velocity of P in I. Again, we have to apply the transport theorem because the basis UR, U theta, UZ is not fixed in the inertial frame. It's fixed in this frame called A, and A rotates relative to the inertial frame. So I have to transport myself from frame A to the inertial frame. So when I take the rate of change here, I get R double dot UR plus R dot theta dot plus, let's take a step back here, R dot theta dot plus R theta double dot U theta. Now that is d dt and A of the velocity of P and I. But I have to add to that the angular velocity of A and I, which is theta dot UZ, crossed with R dot UR plus R theta dot U theta. Now, when you put all this together, you've got R double dot. Let's gather up all the UR terms. So UZ crossed with UR is U theta. UZ crossed with U theta is minus UR. So you get minus R theta dot squared UR. Now, the terms that involve U theta, I've got R dot theta dot plus R theta double dot. But then I've got this term UZ crossed with UR, which is equal to U theta. So I get a 2 R dot theta dot plus R theta double dot U sub theta. Now, to make this tractable as far as the kinetics goes, I have to apply Newton's second law, which I'm going to do next. So the only force acting on the particle is equal to the force of gravitation. And that's equal to minus g little m big M all divided by r squared times ur. Now, in order to make this a little bit easier from a perspective of parameters, I'm going to change the notation a little bit. I'm going to say let mu equal g times big M. So that's going to give me minus m times mu over r squared times ur. So that's the force of gravitation, and that's also the resultant force because there is no other force being applied to the little mass. It's the only force being applied to little m is the gravitational force from big M. So now I know that that has to equal the mass times the inertial acceleration. So that gives me minus m times mu over r squared ur is equal to m times r double dot minus r theta dot squared ur plus 2 r dot theta dot plus r theta double dot u sub theta. So now when I equate components, I get the following two equations. The first equation I get is minus m times mu over r squared equals m times r double dot minus r theta dot squared. The second equation is 0. There's nothing in the u theta direction, is equal to 2 r dot theta dot plus r theta double dot. Now I'm going to simplify a little bit because there's an m in this equation, but the m's going to drop out of that equation. So I dropped it out, but I should have waited one more step to drop it out. So I can divide through the whole thing in both equations by m. So that gives minus mu over r squared is equal to r double dot minus r theta dot squared, and 0 is equal to 2 r dot theta dot plus r theta double dot. Now this is a system of second order equations, right? This is two second order equations. So what we're going to do is we're going to take these two second order differential equations and we're going to transform them into first order differential equations. And here's how we're going to do that. Let's go to the next page and we'll start this whole thing clean, starting with this result that we just obtained from Newton's second law. So repeating what we had from previously, we have r double dot minus r theta dot squared is equal to minus mu over r squared. We have 2 r dot theta dot plus r theta double dot is equal to 0. Now you can see in these equations the variables, at least the variables that define the position. So let's start with that. So the variables defining position. So we have to be real clear that this is only the position. These variables are r and theta. Now similarly, the variables that define the velocity are r dot and theta dot. So when transforming from second order form to first order form, the first thing we do is we take any second derivatives and we have to make them into equivalent first derivatives. So the first thing we're going to do is this. We're going to say we have 4 variables here. You see this. So there are 4 variables total that define position and velocity. So we're going to use all 4 of these variables. So what we're going to do is we're going to start with the 4 variables, and I'm going to make the following substitution. So I'm going to say I'm going to say x1, x2, x3, x4, because I need 4 variables, because I have 2 for position and 2 for velocity. These are equal to, well, the 2 variables that define position are r and theta. So I've got 2 variables there. One is for the first component of position. The second is for the second component of position, or the 2 variables that define the position. Now, for the velocity, I need to use the derivatives, r dot, theta dot. Now you can see that when I do this, I'm not going to wind up having a complete description just from this information alone, because I have second order equations up there. So given that I have second order equations, I need to somehow get this into a form which involves these second derivatives. So the first thing you do is you take the derivatives of all of these quantities that I've defined just now, and we use that information together with the differential equations to describe this in first order form. So I know that x1 dot has to equal r dot, and I know that x2 dot has to equal theta dot, and x3 dot has to equal r double dot, and x4 dot has to equal theta double dot. But if I look at this, you'll see that if I write this down, x1 dot, x2 dot, x3 dot, and x4 dot, this is equal to, well, I know that x1 dot is equal to r dot, but r dot is equal to x3. So that means x1 dot is equal to x3. x2 dot is equal to theta dot, but theta dot is equal to x4. So that means that x2 dot is equal to x4. Now x3 dot, this gets more complicated, is equal to r double dot. So if I solve this equation, so I'm going to leave this for right now, and first thing I'm going to do is I got to solve these equations to get them in the right form. So let's look at r double dot. What does r double dot equal? R double dot is equal to r theta dot squared minus mu over r squared. But that's equal to, well, what's r? R is equal to x1, so that's x1. What's theta dot? Theta dot is equal to x1, so that's x1 x4 squared minus mu all divided by x1 squared. So that takes care of r double dot. Now I'm going to do the same thing with theta double dot. If I solve the second of these equations, if you look up at the top here, I've got these 2 equations. I can label them now. But if I look at the second equation, right, the second equation says 2r dot theta dot plus r theta double dot equals 0. So I can solve it for theta double dot. So theta double dot is equal to, well, what's it equal to? Well, it's equal to 2 r dot theta dot over r with a negative sign. So it's minus 2 r dot theta dot all divided by r. But that's equal to minus 2 times, well, what's r dot equal to? Well, r dot is equal to x3. What's theta dot equal to? Theta dot is equal to x4. What's r equal to? R is x1. So there we go. There are those second derivatives. So now, if I write this out a little bit more neatly on the other side, what I wind up with is the following. I wind up with, let's do it on the next page. So we have r double dot is equal to x1 x4 squared minus mu over x1 squared. Second, we have theta double dot is equal to minus 2 x3 x4 all divided by x1. But we know that r double dot from the equations. Let's go back, and if we look at those equations again, we see that r double dot is equal to x3 dot. And theta double dot is equal to x4 dot. So that gives me a full set of equations now. I can go back and I can combine all these equations. I get x1 dot is equal to x3. x2 dot is equal to x4. x3 dot is equal to x1 x4 squared minus mu over x1 squared. And x4 dot is equal to minus 2 x3 x4 all divided by x1. So now this system of equations, as you can see, it's a system of 4 first order differential equations. Now previously, we had the following system of 2 second order differential equations. So previously, we had r double dot minus r theta dot squared is equal to minus mu over r squared, and 2r dot theta dot plus r theta double dot is equal to 0. So what we did was we took this system of equations and we transformed it into this system of equations. Now it describes the exact same problem. It's just that this system here, this last part that I've written down, is a system of 2 second order equations. So what I did was, by doing the replacement the way I did with these variables, I was able to take 2 second order differential equations and transform them into a system of 4 first order equations. Now, the rest of this now just comes down to how this gets implemented in Matlab. So what I'm going to do is I'm going to show how to write each part of using a solver, say ODE 113, and then we'll go from there, and we'll actually put all this together with ODE 113 and the specifics of how you actually implement this with Matlab by writing the appropriate functions. So that's what we're going to do next. So this is now Matlab implementation to solve differential equations. Now we're doing this numerically, of course. So this is going to be done numerically. So the first thing we need to do is we need to look at, we're going to use ODE 113. Now I'm going to write this out by hand because there's no reason for me to actually go to the computer and code it. You can code it yourself, but I'm gonna actually just write out the elements by hand. So ODE 113, we need the following. We need 1, a function that computes the right-hand side. This is really important. This is the right-hand side. 2, we need a time span of integration. That means that we need an initial time. I'll call that initial time T0. We need a final time. I will call the final time TF. And the span, or the time span, is going to equal T span. This is now MATLAB notation. This is not math. It's going to equal T0 TF. So I have to create a variable. I don't have to create this variable. I can just say T0 TF, but I'm going to do it because I think it's a better way to do things in Matlab. The third thing we need is an initial condition. Now, this is important because this is a vector of initial conditions. We have 4 first order equations, which means we need 4 scalar initial conditions, which means we need a vector of length 4 in order to be able to specify a full set of initial conditions for this problem. And then 4, we need some options for the solver. This is more of a specific thing for Matlab, not or ODE 113. Every one of these is going to be different. It just depends on the particular implementation. And 5, any additional parameters. Now, the additional parameters, in this case, we have one parameter that defines the dynamics of the system. So that's the additional parameter. So I'll put that in here. But let's start first with the differential equations, and then we'll work our way forward from there. So recall, we have x1 dot equals x3, x2 dot equals x4, x3 dot equals x1 x4 squared minus mu over x1 squared, and x4 dot is equal to minus 2 x3 x4 all divided by x1. Now, that means that we need to write a function. So this function is going to be the first input to the call to ODE 113. So the call to ODE 113 is going to be the following. It's going to say Tx is equal to ODE 113. The first thing is going to be the differential equations. I'm just going to generically label this function my ODE. That @ sign just means it's a function handle, which is, we're going to write that function in just a minute. Now I need T span. And then I need an initial condition, which is x0. And again, I'm trying to write this as closely as I can to MATLAB notation so that it doesn't confuse you. But you're going to have to type this in. It's not going to. This is not math anymore. This is computer code. And then we've got data. Now, in this case, that additional parameter is going to be mu. So I need all of these things. First thing I need to do is I need to write this function my ODE. So my ODE is a function whose inputs are time, state, and parameters. The parameter in this case, remember, is mu. It's that gravitational parameter, which I'll talk about in astrodynamics this semester. Now, the time is the current time, so I'm just going to call this thing t. The state is x, but x is equal to all 4 of these things: x1, x2, x3, x4. It's everything. And then the parameters, as I said, this is mu. I already wrote it down. So now let's write this function. So one thing I forgot was the output. So the output of this function is x dot, which is equal to, which corresponds in MATLAB lingo to x dot. It's a variable name. You can't use x dot. You can't have math in MATLAB, so you've got to use a variable name. So we're going to include that as part of this. So here's what this function looks like. Function x dot equals my ODE Tx mu. Now, let's start. Notice that even though there is no time dependence in these differential equations, I still need to have that input x. So now what I'm going to do is I'm going to write out these equations. So here's how I'm going to do it. In order to make sure that I keep consistent with column vectors and row vectors, I'm going to say x dot equals zeros of size of x. So I'm assuming x is a column vector. So this is going to initialize x dot to be the same size as x. It's also going to be a column vector. It's going to be the same length. Now, I can do this a number of different ways, but the way I'm going to do it is I'm just going to go straight for the components. X dot of 1 is equal to x of 3. X dot of 2 equals x of 4. X dot of 3 equals x of 1 star x of 4 squared minus mu divided by x of 1 squared. Well, the order of operations is correct there, so I don't have to put any parentheses around anything. X dot of 4 is equal to minus 2 star x of 3 star x of 4 divided by x of 1. That's the whole function. That computes the right-hand side for me. Now, back in the main file, so that's the end of this function. Now, back in the main file, I need to set up these initial conditions. So I'm just going to give some initial conditions. It doesn't really matter what these are. You can set these to whatever values make sense for whatever it is that you're doing. But the 4 initial conditions I need are r at 0, theta at 0, r dot at 0, and theta dot at 0. These correspond to x1 at 0, x2 at 0, x3 at 0, and x4 at 0. Now, I'm just going to make up some numbers here because it's just easier for me to do it that way, and you can set these numbers to whatever you want when you're solving your particular problem. But I'm going to say mu is equal to 1. So we have a gravitational parameter, or whatever that value, g times m, is 1. x1 at 0, so this is going to be x10. This is now Matlab notation, equals what I'm going to call r0. But r0, I'm going to say r0 is going to equal, well, I'm going to call it rp. And what I'm going to do is I'm going to set rp equal to a value. I'm going to say rp equals 2. Doesn't really matter what it is, and the order of these statements has to be such that you do this correctly. But I'm just sort of schematically getting it out there. Now this is r0, which is equal to rp. x20 is equal to theta 0, and that I'm just going to say is equal to 0. So theta 0 is equal to 0. So somewhere in your code, you also have to have a line that says theta 0 equals 0. So because that's what I'm going to, eventually that's what we're going to use. Now the next thing is we're going to have x3 at 0. So x3 at 0, so x30 is going to equal r dot 0. And I'm going to say r dot 0 is equal to 0. So the initial value of r dot is 0. And then finally, I've got x4 at 0. So x40 is going to equal theta dot 0. Now, this is a little bit more complicated, so I'm going to put it on the next page. So I'm going to say RA is equal to 4. And I'm just going to assign theta dot 0. I'm going to say theta dot 0 is equal to, it's going to be 1 over R0. So if I'm going to do this completely in Matlab notation, it's going to be the square root of 2 over R0 minus 1 over A times the square root of mu divided by R0. Now, what is A? Well, A is going to equal RP plus RA divided by 2. Now again, you have to code all this in the right order in Matlab, but that's going to be the full set of initial conditions. Then what I'm going to do is I'm going to put the initial condition together. So x0 is equal to x10 semicolon x20 semicolon x30 semicolon x40. Now, the next thing I need is I need a time span. So I'm just going to do the time span this way. This is again, I happen to know something about this problem, so that's why I'm picking the time span the way I'm picking it. But t0 is equal to 0. I'm going to say tf is equal to 2 times pi times the square root of a cubed over mu. So that's my final time. So then my t-span is equal to t0 comma tf. And from this, I actually now have everything except for the options. Now the options, the only option I really care about, but it uses a command called odset. And the only option I care about is what's called the relative error tolerance. And that I'm going to set to 10 to the negative 8th. And now we have a full set of information to be able to set up the command in Matlab that runs ODE113. ODE113 at my ODE t-span x0 options and then mu. And that should run the entire process from beginning to end. Again, you have to put the MATLAB statements in the right order. I didn't put them in the right order here, so because I'm not actually coding everything, because if I had to code it, clearly everything would have to be in the right order. But that command, together with the function that I actually gave you, that we wrote a couple of pages back, that command is going to run and solve this differential equation, my ODE, over the time span t-span with the initial condition x0 as I've specified, with the options set for the differential equation solver as specified, and the gravitational parameter mu, which I actually just set equal to 1 for this particular problem. That's pretty much the end of this video. Hopefully that gives you a good sense as to how to go about setting up things in first order form when you're given second order differential equations. I was trying to give you something that was somewhat complete, but without getting into all of the details of coding every last thing, but pretty much writing out most of the code the way you would actually see it in MATLAB. And so that's the end of this video.